everybody who is watching this video. I'm very glad to welcome you. That this is Olenjolai. Possibly it's my first time to welcome you is this fantastic, we call it fantastic gladness. But that's how the life of the man of God used to be. Okay, I would like to welcome you into this fantastic channel against the Tanzania Online A-Level Secondary Schools, Olenjolai M in square brackets, then departments advanced in chemistry. The subject we are studying today is advanced in chemistry, and the main topic is general chemistry, because general chemistry has two topics, which called the atomic structure and the bonding theory. And then the class, this materials has been prepared by using the advanced chemistry syllabus for advanced secondary education in United Republic of Tanzania. So, but the materials may be used elsewhere in the world, might be benefiting, because what we are studying in United Republic of Tanzania is what even some other A-level students or high-level students studying worldwide. But the issue is just the content what you should cover in that case. So, in case you have your seed offering or your thanksgiving for what you've been offering to you, in order to support the cost, the running cost of this program for you to get more videos in advanced chemistry, then you can send your seed offerings in this mobile phone number. The confirmation name is by using the M-Pesa, so the confirmation name is Olenjolai. So we had lecture 9, so today we are going for the lecture 10, and I would like just to do the quick review of what we have covered in lecture 9. So I can link means that in lecture or in session 09. So in session 09, I taught you the concept which is called the Hansen-Badge uncertainty principle. So that's the whole concept. And this physicist, he has been that a German physicist, he's a German physicist, he said that it's not possible to do what? To predict what? To predict boss what? Position and what? Position and the velocity of what? Of a negatively charged subatomic particle called the electrons in the atom. That's what he said. And then he established mathematical equations of relationship. He said that change in position, then multiplied by change in the momentum of electrons or velocity of electrons, this is approximately equal to the Planck's constant over 4 pi. Fantastic. And then we solved some problems. We explained into too much details, but near the end of this lecture, I have touched a little bit about it, the equation now, which can predict it can give us the maximum probability where we do find what? We do find the electrons in an atom, which is called the Schrödinger wave equations, which is beyond to this level. Okay? So if that's the case, if you didn't watch the session 9, make sure that you watch before this session 10. So if you are happy right now, join me in the session 10. Okay? So session 10, we say that I'm going to teach you the concept called the wave duality nature. These concepts are very important. You will find them in the final exams, in the mock exams, in the midterm exams, in the annual exams. You will find this concept. I insist you, make sure that you understand them clearly. The wave duality, the wave particle duality. So this we call it, I'm sorry, I made a mistake in this subtitle. Let me just correct it, because the chemists, they can punish me, they can give me penalty. Wave particle, say it, wave particle duality nature, wave particle duality nature of what? Duality nature of electrons. Okay, of electrons. So what the meaning of the word duality? Duality, this the word comes from the word known as duo. Duo, it means two, right? So the physicists, again, the French physicist called Louis Victor de Broglie, did a lot of experiment concerning about the nature of electron. After his experiment, he said that an electron can be considered as a particle. Why? Because it has mass, okay? Then it has what? It has velocity, right? And also it has positions and so forth. But again, after doing too much experiment, he realized that an electron also can be considered as what? As a wave. Why? Because it has wavelengths, it has, we call it a frequency, you see? And then some other wave properties. So that's why that we have this concept called the wave particle duality. So wave means that an electron can be considered as a wave. Why? I will tell you in details. And also an electron can be considered as what? As a particle. So that's the good news, my dear student. Okay, so let us go to the business right now. Okay. So we say that I would like to start with this man who introduced this concept for the first time, Louis. This is the French name, Louis. Louis Victor de Broglie. De Broglie was the French physicist, not the chemist, French physicist. Who did many experiments. He was a theoretical, we call him theoretical physicist. He was the French theoretical physicist. So he did it, or who did detailed study on the nature of what? Of electrons. So now we can state the concept or his belief or his finding that according to, so we say that so the question is state Broglie model. So he said that according to de Broglie, we say that all material objects, all materials objects are dual in nature. That is they exhibit both wave and the particle characteristics. This is the Broglie wave duality nature. So all material objects are dual in nature. That is, they exhibit both wave and particle characteristics. So this is the end of quote. Right? What does it mean? because he has been doing investigations on the electrons, it means that the electrons has both properties. Electrons can be considered a wave and also can be considered a particle. Right? That's what he's saying. That's what they believe and that they prove. Having things like mass in electrons is a particle characteristics, while having things, wavelengths and frequency is a wave characteristics. So he said that if example, particle characteristics, right, of electrons are this. First one, because does electrons has mass? Does electrons have mass? Yes, it has this mass, and this is called mass of electrons. And we might even get the mass of electrons from the scientific calculator, right? So by using the back cover, so you press constant 0.3 m subscript of E. So it means that this one we might get it by pressing constant 0.3 in scientific calculator, then we get mass of electrons is equal to what? So constant 0.3 mass of electrons, it is 9.1 exponent negative 31 kilogram. That's why we do consider these electrons as what? As a particle. So that's the particle characteristics of what? Of electrons. Okay, particle characteristics of electrons. The second particle characteristics of electrons, we learned it in the lecture 9, or in session 9, where we have learned about what? We have learned about velocity, right? So we say that charge and momentum about what? So the other ones is momentum, right? So momentum depends, right? Momentum of what? Momentum of electrons. So in momentum, for example, that we talk about linear momentum, we say that this is mass times velocity. So for instance, in Hansen-Bethe uncertainty equations, we say that, for example, momentums you can determine from these expressions. Planck's constant for pi times what? Change in position. So it means that the electrons, there's what? Momentum. Right? So that the second characteristics to say that, or the de Broglie found and say that an electron is the particle. But the third characteristic is a charge. Say charge. Charge. So charge, this is Q in notations. Does electrons have a charge? Yes. What the charge of electrons? So the electrons, there's a negative charge, which is negative 1.6 exponent negative 19 Coulomb. Coulomb. So this is capital C, Coulomb. Negative 19, capital C. Coulomb. So negative 19 Coulomb. Okay? So this is the unity for the charge. So that the quantity of quantity of charge. In a scientific calculator also, you can determine the quantity of charge. The quantity of charge as you press the constant and then you go 23. So constant 23, you get the quantity of charge. So it means that in scientific calculator function, this is function 991 that if you don't have, please go to the descriptions of this video and then you can order the original scientific calculator. So constant 23, so F991, so constant 23, you'll get the quantity of charge which is labeled as what? As electrons. Right? So those are the three characteristics that make an electron to be considered as what? As a particle. So let me take you to the other characteristics, other three characteristics. There are many, but I've just mentioned three. You can find the rest of the characteristics. So characteristics We say that the wave characteristics of what? Of electrons in an atom. Right? So we say that electron is considered as the wave because it has or it possesses these characteristics. The first one, an electron still has what? Energy. It has the wave energy. And this energy is given as what? So it means that this energy we can compute from what? From Planck's equation. From Planck's what? Mathematical equation. Where that he said energy is very proportional to the frequency. So energy is equal to Planck's constant times frequency. Right? So an electron possesses energy. And this energy is not calculated maybe by using mass and velocity of electrons. No. This energy is computed or is calculated by using what? This energy is computed by using the wave properties, okay, which is frequency, and also sometimes you can compute that energy by using the speed of light and even what? Okay, so the second property is an electrons is also considered to have what? Speed of what? Of light. Energy because we have the speed of light. So traveling, so an electron is considered as traveling with the speed of light. But I'm not sure about this property. So an electron is considered as a wave particle because it has frequency, right? That's why it emits radiations in particular bands because of the frequency. And this property of frequency also, or we learned it in previous lecture, are from Planck's law or Planck's equation. State that energy is very proportional to the frequency, and this implies that change in energy is equal to Planck's constant times frequency. And what is frequency? Frequency, this is speed of light of what? Wavelengths. So before I explain this one, this is now. So we mean that the frequency of electrons, it can be computed from this expression, right? So this is the expression for computing the frequency of electrons. Again, we learned that an electrons, it's a wave particle because it has what? Wavelengths. Right? Wavelengths is notations is lambda, frequency notations is frequency. So wavelengths. So where do we get this? We get in many cases. For example, we say that from Rydberg equation that I taught you in previous lectures, we say that 1 over wavelengths is equal to Rydberg constant times 1 over lower energy level square, then minus what? 1 over higher energy level square, like this. So this is the wavelengths that we've been talking to. But also we can find the wavelengths of electrons of a particle, whatever that is, from what? From Planck's equation. So from Planck's, what did he say that? He said that change in energy is equal to Planck's constant times speed of light over wavelengths. So this will make that the wavelengths is equal to change in energy. No, is equal to Planck's constant times what? Planck's constant over change in energy. So this is the formula for finding the wavelengths of an electrons. Right? So up to this moment, you believe that an electron has a nature of particle, and also an electron has a nature of wave. So that's why that we broadly confirmed that electrons possess both wave and particle nature. And those are the facts according to his mathematical equation. So again, we say that according to de Broglie, now we can combine two mathematical equations to make one equation that describe what is a wave particle duality of electron. So the first equation is Planck's equation. The Planck's equation, Planck stated the law that the NH is very proportional to the frequency. So the NH is equal to Planck's constant, which we've been discussing in this topic frequently. So this is the first equation. Again, the second equation we call it the instant. The instant equation. So the instant equation, the instance equations. This is I'm introducing in this topic for the first time. So the instance equations. So I would like just to go slowly, so for you to understand it, is given as the NH of the photon. Say NH, so photon. Say photon. The energy of the photon is given as mass times speed of the light. Right? Einstein did many experiments on the photonic concepts, and and he used the atomic structure also to explain his concept. Okay? So remember that here, this is energy, this is Planck's constant, this is frequency. This is energy, this is mass, this is what? Speed of the light square. So basically, according to the concept that I've been teaching you, this is wave characteristics, or this is wave equation. The Planck's equation is the wave equation. And then this is what the particle equations of electrons. So bear that in your mind. Particle equations of of electron. Right? So we can combine them and then formulating a fantastic mathematical equation. Okay? So if that equation 1, then we go to, let's say that the first step. Suppose that this is the first step of deriving this equation. And suppose also this is the second step, right, of the deriving equation. Then we can go to the third step. So the third step, we say that let us equate equation 1 and 2. So if we equate equation 1 and 2, then we say that Planck's constant times frequency is equal to mass times, so in case of electrons, this is the mass of electrons. Mass of electrons times square of the speed, right? So then, if that's the case now, we say that this is what we call the, first of all, this this equation, we call it what? So this equation is called what? So it's called the what? It's called the Einstein-Planck's equation. Einstein-Planck's equation, right? But also we say that this the first step. We say that from the speed of light is equal to the speed of light is equal to wavelength times frequency. So on this left side, it means that we can express frequency is equal to speed of light of our wavelengths. So on left hand side, we can replace frequency with what? Speed of light over wavelengths. This is equal to mass times speed of light. So then, if we simplify, or even without simplifying it, but remember that this is the speed of electrons, okay? What is speed of electrons? So what is speed of electrons? So that the case, okay? So then this also equal to wave water. So this we call Einstein-Planck's equation. Okay, so then we want to come to the concepts of what of de Broglie now, of establishing a mathematical equation which explaining the wave characteristics of electrons and the wave characteristics of electron and the particle characteristics of electrons. So from this equation we say that we have Planck times speed of light over wavelengths is equal to mass times speed of light squared. So let us make the wavelengths the subject. So this will be the fifth step. So the fifth step we say that make wavelengths subject. Make wavelengths the subject. So to make wavelengths the subject, we say that this is Planck over speed of the light over mass square is equal to wavelengths. So I multiply by wavelengths both sides and then divide by mass times speed of the light. So we simplify this and this. So wavelengths is equal to Planck's constant over mass times speed of the light. So you see now, this is what we call the de Broglie equation. So then we have derived de Broglie with vectors de Broglie equation. So the Broglie equation now is a combination of of Einstein mathematical equation, Planck's mathematical equations. So this is mass times speed of the light. So this is why we call it the Broglie equations. Okay, speed of light is constant. See, speed of light is constant. Planck's constant is constant. So what is a unique notifications or unique identifications of this? Why do we physicists and chemists call it the Broglie equations? There are two physical quantities which are not constant, right? The wavelengths, which is representing wave characteristics of electrons, the mass, which is representing particle characteristics of electrons. So remember that the concepts of de Broglie, or even the Broglie's postulates or models, he was saying that an electron possessing both particle characteristics and wave characteristics. So that's why this is very important mathematical equation in atomic structure. Do you like it? Save it in your mind, right? Yeah, so make it your friend. So the wavelengths we determine there also in physics or in atomic physics or in atomic science are the scientists or the other physicists, they gave the name of the wavelengths we determine from that formula the Hahn of de Broglie. Right? The Hahn of de Broglie. So we say that the wavelengths, okay, the wavelengths calculated by using de Broglie equation equation, and this is wavelength is equal to lambda over mass times speed of light, is called what? This is called the de Broglie wavelengths. So when you find your questions asking you that calculate de Broglie wavelengths, don't panic. Tell it, yes, you are my bestie friend. You are my bestie friend. You, de Broglie wavelengths, you are very simple to me, right? Tell it, speak to it, and then make sure that you find that de Broglie wavelengths, right? When you find, you get out in exams are the victors. So from these de Broglie wavelengths, we can deduce something, or we can speak, or I can explain something in a minute. One thing which I want to tell you that from these de Broglies we find, first of all, the wavelength is inversely proportional to the mass of the atom of electrons. So remember the mass of the particle or mass of electrons is constant, you see. So it depends, because these equations is used in different scenarios, but we are studying the concepts of atomic structures. So the Broglie's wavelength varies inversely proportional to the mass of an object, which means that when the mass is large, the de Broglie wavelengths become very small and therefore immeasurable. In other words, the Broglie concept is useless for macroscopic objects like what is stone, because with large mass, the de Broglie wavelength is too small to be measured. So the Broglie wavelength is used for microscope, for the small particles. So the Broglie concept is significant for microscopic objects like electrons, whose mass is very small. You remember the mass of electrons? I think that they mentioned here. Yeah. So it means that because the mass of electrons is very small, because remember that this formula is applicable. It's applicable even to find the wavelengths of the stone, but it will be meaningful if you calculate the wavelengths of the stone. So the limitation of this formula, we say that the mass of the object should be what? Should be very, very, very small for the Broglie wavelengths to exist, right? That's the concept that I wanted to make. Any questions concerning about the Broglie, you may ask it in the comment section. Do you enjoy advanced chemistry? Is it beautiful? Do you enjoy these mathematical questions? Have you ever seen them? Did you learn them in your level studies? Did you learn them in primary school? No, this is the first time. Enjoy them and keep them in your mind. Okay, so if that's the case now, we say that we have one phenomenon we have defined, and so we do one problem, then okay, we'll call it a day, for just to say that at the end of the lecture, right? The term now we want to define is well defined, or it has been discussed by Sir Einstein, and the concept, Sir Albert Einstein, right? The concept is concerned about the photoelectric effect. This concept of photoelectric effect is too much. Remember that the concept of atomic structure also is well discussed in atomic physics, or we call it modern physics. So if you are pursuing physics, right, you are doing physics in your A-level studies, believe me, we learn similar concept like this in atomic physics or modern physics at the Form 6 topic. So when you understand this material, keep in your mind. You can go through even that subtopic, because atomic physics, it has 4 subtopics, right? The atom, or the atomic structure, and then there's these issues of instance, okay? The instance, and then there's another concept, we call it radioactivity, and then the other concept concerning about the X-rays and the gamma rays and so forth, especially the X-rays, because gamma rays is a part of radioactivity. Okay, so make sure that you keep this material as long as you learn. Now the term that I want to touch a little bit, which you can be asked in chemistry, however that's not frequently, but in physics is normal, photoelectric effect. Say photoelectric effect. Photo what? Electric effect. Photoelectric effect. Photoelectric effect. Photoelectric effect. Photoelectric effect. Photoelectric effect. Photoelectric effect. So the question is this: what is photoelectric effect?